Today I will going to present our paper titled Towards a Secure Zero Rating Framework with 3 Parties. This is joint work with Zheng, Professor Cao, Zhaohan, Shihao, and Dr. Humberto Larache. So one day I was out of town for traveling, but accidentally got a message from my advisor that he needs some experimental data from me. So in order to send him the data, I need to connect it to this experimental server and do the experiment, get the results, and then send it back to him. Well, although I keep my laptop with me, but there is no Wi-Fi around me. So in order to access to my server, I need to use cellular network data. I start as hotspots, but unfortunately, I have already run out of my data plan during traveling. So I only have a very low network speed connection with the internet. Then I have to wait the page loading and also the connection established with my server. Unfortunately, I will get a time out of error. Well, the interesting thing here is, as an T-Mobile user, that I can still have some access to some web services in a relative high speed. For example, YouTube. The reason is that those web services are contracted with T-Mobile and they are included in a service called Bingzhang. And when I'm visiting those Bingzhang services, the data emit won't be charged. That's why they call such kind of services as zero rating service. And I will start to think about, is that possible that I can pretend to visit those zero rating services, but actually visiting something that I want? Here, for example, I want to visit my Gmail and also my server. The answer is yes. So we can fool the ISP set and to get unlimited data access to other services than zero rating service. This kind of attack has been titled as free riding attacks. And in the rest of the talk, I will first talk about how we can launch free riding attacks on industrial system and other prototypes. Later, we will talk about how we can defend against such free riding attacks. So before we talk about specific free riding attacks, I would like to emphasize our threat model of free riding attacks. There are 3 parties inside our threat model. That's why our paper titled with 3 parties. In our threat model, that clients is malicious here because clients are someone who wants to get free network traffic, where ISP side and content providers are benign, and it could be victim. While some charged content provider, because they can masquerade as a zero-rated content provider. So those charged content providers are potentially malicious. So let's talk about 2 types of free riding attacks. I will introduce 2 types of free riding attacks on industrial system and 2 other specific attacks on academic prototypes. So I would like to talk about request masquerade attack on existing industrial system. In this attack, client side, malicious client will send a request packet to the attacker server, which attacker server is a non-zero rated content provider. While the noticeable change here is it uses a domain name actually belong to a zero rated content provider, YouTube, for example. While this request packet can still received by the attacker server because it uses the destination IP belong to the attacker server, and the connection can established. Once the connection is established, this connection will be tagged as zero-rated connection. Here, attacker server can act as a proxy, so you can basically have any web services accessible. So the next type of attack, called response modification attack. In this attack, the main idea is to inject non-zero-rated content into the response packet. The process goes following. The malicious client will first build a connection with a truly zero-rated content provider, but later it will launch a man-in-the-middle attack in between our ISP network and the content provider. Inject those non-zero-rated content, and those content can be received by the client side, so that's why we call it response modification attack. And there are two types of zero rating service system other than existing industrial system. One called network cookie, and another is IP whitelist based method. For example, Facebook Zero. We will briefly talk about how those system works and how we can compromise those zero rating services. In network cookie, it uses a cookie to differentiate zero-rated traffic. Once the client builds a connection with a zero-rated content provider, it will get a cookie. And later communication, that client will always present this cookie. So ISP side can differentiate zero-rated traffic with this specific cookie. While this cookie haven't bind to any data-specific connection, so the malicious user actually can present this cookie for any network connections. In here, referred to red lines, it can visit a charged content provider, but also present this cookie. So the red lines will also be zero-rated. So next, in the IP whitelist-based method, here, for example, Facebook Zero is one of them. In this method, that there are an IP whitelist inside the ISP network side. So ISP can differentiate the response packet based on the source IP address inside the response packet. Well, in order to compromise this system, the client, malicious client, will first build a connection with the zero-rated content provider. Once the connection is established, it will send the information of this connection, this zero-rated connection, to attacker content provider server. The information include source IP address of the zero-rated content provider and ACK number and sequence number of the last packet it received from the zero-rated content provider. With those information, an attacker server that is non-zero-rated can forge the response packet, act as a zero-rated content provider to the ISP network, and those packets without being dropped by a network. So we can compromise these IP whitelist-based systems. And zero-rated content provider here become a victim. So in conclusion, that we performed free-riding attacks against 5 industrial systems and 2 academic prototypes. The header of the table indicates the name of each system, which includes 3 of them are mobile network, 2 include T-Mobile, China Mobile, China Unicom, and 2 of them are airport Wi-Fi, include United Wi-Fi and Chicago, Ohio airport Wi-Fi. And the rest of 2 are academic prototypes, network cookie, and IP whitelist-based method. As we can see in the table, none of those systems are robust against free-riding attacks. Cross means they are vulnerable. And some cells fulfilled with non/A is either because that system doesn't allow us to use encrypted data or unencrypted data. And based on recent report of global internet phenomena, that a major US network carrier could lose over $7 million in a month by such free-riding attacks. And based on our analysis of traffic from China Mobile, that they can lose over $500,000 in a month only in one province in China. And in order to get this estimated number, that we first filtered abnormal users. Those abnormal users consumed over 3 gigabytes zero-rating service traffic, and we manually inspect those unencrypted data part of those zero-rating traffics, and we found over 71 terabytes free-riding traffics. So it is a serious problem in industrial. So let's come to our system design to defend against such free-riding attacks. So the root reason of existing vulnerability is that ISP side cannot verify the integrity and authenticity of a response packet comes from content providers. So in our system design, we have 2 pluggable modules. We call them ISP assistant and server agent. Those two components are backward compatible. They won't affect underlayer protocols. And those two components talk with each other through a Z-free control plane protocol. The server agent at the content provider side will accept the mirrored traffic from the content provider network, so it knows which specific packet goes out, and it will generate keyed hash value for those outgoing response packets. Then send those keyed hash value to the ISP side. ISP assistant thus can use those keyed hash value as identity for those response packets to verify the authenticity of those response packets. ISP assistant runs in blocking mode or non-blocking mode. In blocking mode, ISP assistant will temporarily block the connection between clients and the content provider, which is useful for content control system. For example, in airport Wi-Fi, you only want user to visit certain websites, include car rental websites or ticket booking websites. So let's take a close look at ISP Assistant internals. There are mainly 6 modules inside ISP Assistant. It first will establish a connection with a server agent, and next it will get key hash value from the server agent, so it knows which specific response packet goes out from a certain content provider. At the same time, it will accept the key mirrored or redirected traffic from the ISP network and pass those network traffic to generate a keyed hash value for each network packet it received. Use an HMAC algorithm, which the key is shared with the server agent side, so it can generate exact same keyed hash value for same response packets, and send it to the integrity checking modules, where integrity checking module maintain 2 databases to save those keyed hash value haven't been matched. Once a packet can be verified the authenticity, it will send back to the ISP network if it runs in blocking mode. And at the same time, it will telling the charging system which specific response packet should be 0 rated and how much is the volume. In the server agent side, it will get the mirrored traffic from the content provider network, so it knows which packet goes out. And it will pass those traffic and generate keyed hash value, again use HMAC algorithm, and send those keyed hash value to hash module, where hash module will control how to send those keyed hash value to ISP assistant side, either in real-time way or it will send in batch mode. The message will use a Z-free control plane protocol here. So to prove that our system is secure, we use a tool called Probative. It is an automatic protocol verifier that we need to first build system model for the system we want to verify. The header of the table indicates the name of each system, and the leftmost column indicates the verification goals that we want, which include we want to verify the packet integrity, because in this case that no attackers can inject non-zero rated content without being detected. And we also want to verify the content provider authenticity, so no attacker's server can masquerade as a 0 rated content provider. And we also don't want to compromise users' privacy, so we want to verify the data secrecy in here. And as we can see in the table, only Z-free under encrypted data communication type, the rightmost column, 3 verification goals satisfied. Thus, we proved that Z-free is secure. And come to implementation, that Z-free include 1100 line of code for ISP assistant implementation and 790 line of code for server agent implementation. We have 2 types of network facilities to evaluate our system, and we have 1680 lines of code for building the verification model. To evaluate our system, we start with the airplane Wi-Fi, where we use mininet Wi-Fi module to simulate the airplane Wi-Fi, and in this network, we have 120 user equipments inside our network, and those equipments connected with 2 access points. The central router here as an ISP, act as an ISP. And we have simulated content provider to provide network services, web services, actually. We have another network setting for LTE network. We use an S3 to simulate. We simulated 1,200 user equipments inside this network and 2 base stations. While comparing with the airport Wi-Fi, the user equipment inside this network is moving with a random speed ranging from 10 to 120 kilometers per hour. During those user equipments moving with random speed from base station 1 to base station 2, it will temporarily connected with both base station 1 and 2. It will finally connected with base station 2. This process called handover, and it will affect the transmission rates. We want to know the overhead of our system during handover process. To show our experimental results, we first start from the user's perspective. We use loading time to indicate the usability of a network. And we use a content provider as network proxy. At the client side, we visit top 500 Alexa websites to get the average page loading time. As shown in the graph, the x-axis represents the loading time in seconds. Y-axis represents the cumulative probability. As shown in the graph, the system with the free non-blocking mode refers to a green dash line, which are stay close together with the normal axis, which refer to blue dash line. While blocking mode of the free incur a little bit worse, more overhead, but still less than 9%, which refer to the red line. Next, in order to know the overhead of during handover process, we measure the transmission rate differences with or without the free when user equipment is moving with a different speed. Here, the x-axis represents the user equipment moving speed in kilometers per hour, while y-axis represents the transmission rate in megabits per second. The system with the free refers to gray bar. As we can see, it only incur ignorable overhead here. So next part, we start from the ISP core network perspective that we want to prove the scalability of our system. We choose a bandwidth 150 megabits per second, which is commonly used in commonly used in LTE network. And we gradually increase the number of connections between clients and content provider. As shown in the graph, that x-axis represents the number of connections, y-axis represents end-to-end delay in milliseconds. And as we can see in the graph, that TLS encrypted connection always has a higher end-to-end delay comparing with TCP connection, while the system with the free, referred to green and blue lines, stay close together with red and CN respectively, which proves the scalability of our system. To evaluate our system to prove that our system is durable, we performed a stress test lasting 5 hours, where we replayed the network traffic captured from real network traffic from TCP replay and net traffic. And to simulate the bursty traffic scenario, we speed up the packet replay process every 30 minutes. The peak network speed is ranging from 8 to 10 gigabits per second. As shown in the graph, the x-axis represents the lasting time in minutes, and left side y-axis represents the actual throughput of the network. And the system with the free referred to blue line, which they follow exactly the same pattern with the legacy mobile network, and which proves that our system won't cause the bottleneck when network speed is under 10 gigabits per second. And the green dash line referred to the ISP CPU usage of ISP assistant, which never exceeds 80%, which proves the computational efficiency of our system. In order to prove that the free is practically secure, we performed 3 free writing attacks, where retransmission-based attack is that the attacker will send the retransmission attack, but with different content inside those retransmission attack. And we are sure that none of those free writing attacks can penetrate in our system. Thus, Z3 is secure. In conclusion, that we launched free writing attacks against the real-world system, and we found the vulnerability of existing zero-rating services. Then we proposed and implemented a Z3, secure zero-rated, and backward compatible, and it is scalable framework. We formally proved that Z3 is secure, and our evaluation results shows that Z3 is only incur ignorable overhead, and it is scalable. So for further details, please refer to our paper and our code repository at GitHub, and we also have an online demo to demonstrate the usage case of our system. So thank you for your patience. Yeah.
All right.
Yes.
I'll ask a question.
Sure. Yeah, thank you.
So a lot of the system requires coordination with the content provider. So kind of before it was kind of a little bit more transparent. They didn't have to like modify their own system to be able to participate.
Yes, because it is backward compatible, so you don't need to modify any code base at content provider side because we only use mirror traffic from the network.
But it seemed as if there was required control plane connection between the content provider.
Control plane is happened with server agent and ISP assistant, which is code base from our system, so it won't affect the old code base of content provider side or ISP side. Yeah.
Any other questions? Well, let's thank the speaker one more time.
Thank you.